Hello and welcome to fourth lecture in 19th chapter in our comprehensive course on artificial intelligence, machine learning and data science. Now, the name of this chapter is this Introduction to Basic Statistics. And I told you that there are three clear parts in the chapter. First part is descriptive statistics, second part is understanding distribution, and third part is inferential statistics. We are at present doing descriptive statistics. In fact, as such, we have almost completed all these things: mean, median, mode, variance, standard deviation, like this. So we have to start from here. Applications in data science. What is the use of these descriptive statistics? So first line says that descriptive statistics provides foundational insights into the data and helps us understand central tendency and variability. Now, for example, when we create a data frame using a dictionary and then use the pandas.data frame, or whenever you import a CSV file using panda.read_CSV and then save it as a pandas.data frame, whatever. But once a data frame is obtained, then immediately we write ds.describe. What this describe will give is statistical summary of all numerical variables. Right? Okay. But similarly, thereafter, there is one another in which you can write here include equals object. So what that will give is statistical summary of all categorical variables. Okay, and if you write include equals all, then in that case you will get statistical summary of both numerical and categorical variables, that is all variables. Also, what do you get in that statistical summary? If you remember, you get mean, then you get median, then you get 25th per quartile, percentile, 50 percentile, then 75 percentile, then you also get maybe I think maximum value, minimum value. So that means you get the range indirectly, and these quartiles, they are interquartile distance can be obtained from this, and mean, median, they are the measures of central tendency. You also get standard deviation, which is the measure of dispersion, and so on, right? So this is what we already know. Now, if I read this sentence now, then it becomes clear that descriptive statistics provides foundational insights into the data. It gives so much information, helping us to understand the central tendency and the variability. This is crucial for data pre-processing, because if you find that the scale of various different columns or the features in your data set is varying a lot. For example, three columns are there. First column is salary, in which the salary varies from $25,000 to $85,000. Next column is the age of employees, so which is say 20 years to 60 years. Then next column is suppose the seniority of the employee in terms of number of years of service. Then that varies from maybe 0 years to 30 years. So age and the seniority, they are varying over very small ranges, while salary varies over very large ranges. So that gives us idea that what data pre-processing you will do, you will have to apply scaling or normalization. We have done very detailed discussion about that. So we know that there is a standard scalar and there is a min-max scalar, and we bring all the things to same level. Similarly, we can get idea about exploratory data analysis and which plots would be more useful, and feature engineering. So that will help in better model accuracy and interpretation. Now you know why this chapter is here, because immediately next we want to do this feature engineering and model creation, and then we obviously would like to create an accurate model. So then that will be, you will be able to do that provided you have studied your data in depth. Okay. Now we did everything in this previous discussion lecture, that is mean, median, mode, then variance, then mean absolute deviance, then deviation, then standard deviation, then maybe interquartile distance, and all those things. Now we want to talk about one or two extra topics. They are extra topics, but they are quite important topics. For example, this is one topic, Chebyshev'S Theorem. Okay. Now this theorem is very, very important, because that teaches you a lot of things that whenever we do, for example, outlier removal, or whenever we do capping to bring the data within the acceptable range, then why that thing is statistically valid? Why we are not doing anything just randomly or in a present manner violating different rules? That assurance you get from this theorem. We will not go into the proof of the theorem, because proof is not important, but its applications are important. So for any set of numbers, and regardless of how they are distributed, now these two sentences are very important. So any set of numbers is my data set. For example, this was my data set earlier. We had seen this, okay, a collection of many numbers, right? So for any set of numbers, and irrespective of their distribution, may it be normal distribution, may it be non-normal distribution, may it be exponential distribution or logarithmic distribution, or maybe uniform distribution, or maybe it is say Poisson distribution, whatever. So this result is very general. Howsoever data points are distributed on xy plane, for simplicity I am taking only two variables, x and y. Y is the dependent variable and x is the independent variable. Howsoever two points are, howsoever the points are distributed, the fraction of the points which lies in, here it should be that lies within k standard deviation of their mean is at least 1 minus 1 upon k square. 1 minus 1 upon k square. This is square. So if I write it, then this is how it is. Okay. So then what is the meaning? So let me put some values to my k, then it will become clear. So this is that same statement only. Again I am reading, for any set of number regardless of how they are distributed, the fraction of them which lies within k standard deviation of their mean is at least 1 minus 1 upon k square. So for example, I have one such one such data distribution. For example, say this kind of data distribution, which is not even normal distribution, just maybe this kind of distribution. Okay, then its median or mean is somewhere here. Now here mean and median will not be the same. So I'm talking about, say, the mean value, and the mean is given by this line. So this line that gives the mean. Okay, this is my x-axis. So this much value, that is my mean value here. Okay, that means this is mu, sample mean. Now if someone asks that I take this much distance, which is equal to 1 standard deviation, so k is equal to 1, then someone says, no, I want to take this much distance from mean, which is equal to 2 standard deviation, 2 times sigma. I'm writing with mouse, so apologies for a little bit unclear. Someone says, no, I want to take distance equal to 3 standard deviations. Okay, so that is this 3 sigma, and still someone says, I want to take distance equal to 4 standard deviations, or that means this is 4 times sigma. Then in that case, how many percent of data set will be accommodated? So that means here there are many different data points. This entire region below the red colored freehand graph, that is filled with this kind of data point. Now the question is, how many fraction, what fraction of data will be accommodated in 1 standard deviation distance, 2 standard deviation distance, 3 standard deviation distance, and 4 standard deviation distance. So that means 1 standard deviation distance, when I write, that means what? That here k equals 1, because the Chebyshev's theorem is for any k standard deviation distance. Similarly here k equals 2, similarly here k equals 3, and similarly here k equals 4, right? So then the theorem says that howsoever is the distribution, normal or non-normal or whatever, if I take k standard deviation distance, then 1 minus 1 upon k square, that many percent of fraction of data is enclosed within that much region of data distribution, and that is at least. So that means it can be more than that also, but at least 1 minus 1 upon k square. Let us take some number, then it becomes clear. For example, if someone asks what fraction will be embedded or enclosed within 2 standard deviation distance, then I will write that it is 1 minus 1 upon 2 square. So 2 square, k is equal to 2 here. So then 2 square. So then 1 minus 1 by 4, 3 by 4. So 0.75%. So you can say that fraction of total data point which will be included in 2 standard deviation distance would be 75%. Of course, you have to remember that it is 2 standard deviation on this side also and this side also. That total region that will accommodate 75% data point. If I take 3 standard deviation, means k is equal to 3, then it will be 1 minus 1 by 3 square. K square will be 3 square, or that is 1 minus 1 by 9, 8 by 9. So 88.88% of the data point would be accommodated in 3 standard deviation from this side to 3 standard deviation from this side. And if I take 4 standard deviation, that is k is equal to 4, or the 4 sigma distance, then in that case it will be 1 minus 1 upon k square, 4 square 16, or 15 by 16. So that is 0.9375, or that is 93.75% of my data points are distributed here. And if I take 5 standard deviation distance, then it is 1 minus 1 by 25, or that is 24 by 25, or that is 0.96, or 96% of the data points, they are located within this distance. Is that clear? Okay. So this theorem is very important theorem because it is applicable not only to normal distribution, but it is applicable to all kinds of distribution. Okay. Now this is one example that take data points, and deliberately the diagram has shown a bimodal type of distribution that is not normal, so that impression should not go in learner's mind that Chebyshev's theorem is only for normal distribution. It can be applied to any distribution, right? So this is the mean point, mean of sample, okay, and there this is one standard deviation, two standard deviation, three standard deviation. In two standard deviation at least 75%, and in three standard deviation at least 88.88, or that is 88.89% of the data points are located. Okay, so this is important, and for normal distribution it is really even perfectly applied. So one standard deviation 68%, two standard deviation 95%, and three standard deviation 99.7%. This rule is called empirical rule. This is not Chebyshev's rule, but it is specially derived for normal distribution, that is bell curve, and it is called 68, 95, 99.7. Okay, so if that is the situation, then that is the reason why we try to look for normal distribution. And if normal is not there, like this for example, then also we try to do some mathematical or data transformation tricks to bring it as close as possible to normal. Because in normal distribution, you can see that if I take distances up to 2 standard deviation, then 95% of my data points are included. And that means I can remove this region, that is this region from on the left side of this vertical red line, right? That is this whole region. That many data point I can remove. Similarly, I can remove that many data point on this side also, and therefore I can keep only the data point between -2 standard deviation and +2 standard deviation. It will still include 95% of the data point, or that means I can say that the confidence interval of my results would be plus or minus 0.95 or 95% confidence interval, because or error would be confined to plus or minus 5% at the most. Okay. Now, this is very important, and this is the basis of removing outliers on the basis of standard deviation. We know that outliers can be removed by either IQR, interquartile range, but outliers can also be removed on the basis of standard deviation. That any data points which are here, where my cursor is at present, this, okay, they are more than 2 standard deviations away, so remove them, all those data points. And similarly, any data points which are here, they are also more than 2 standard deviations away, so remove them here. Or if you can't remove them because of some specific application like answer detection or credit card fraud detection, that is a different thing. But in other case, when you can remove it, then for example, this is age distribution graph. So if age is so high compared to 95% of the data point, then that observation you can remove, or you can cap it and bring it within this, okay, within this. That phenomena or capping, that is called Winsorization. Okay, we say that we cut off the extra point and bring the data, its value we cut off, and we bring it within the normal range. Now, what is the real world application? So I have taken one very practical and very interesting example. Now suppose you have designed some killer mobile app, and you want that mobile app to be downloaded from your server, assuming that Google Play and all those restrictions are not required. So suppose you want to put your own server, and from that you want to allow the downloads. Now the question is how much capacity server you will put. For that you will have to ascertain that how many downloads will occur in one day. Okay, so and because if more downloads will occur, then you will have to provide higher capacity server, more bandwidth, and so on. And if less downloads will occur, then you will have to provide lesser capacity server. So here we try to do this by this way, that suppose we have observed the daily load for a few days, say 100 days, and you have found that the data points vary with a mean of 50. So that means on an average, mean downloads are 50 with a standard deviation of 8. So that means on an average 50 downloads occur. Then one standard deviation means on this side 58, and on this side 50 minus 8, so that is 42. On this side still another 8, so that is 64, and on this side another 8, so for another 8 minus, so that will be 42 minus 8, 34, and so on. Okay, now find the probability with which we can assert that there will be more than 34 but less than 66 downloads in a day. So that means you are saying that download will be more than this point, because this was 34, this was 42, this was the mean download, that was 50, this was 58, and this was 64. So you are saying that, sorry, 58 and 66, right? So you are saying that the download will be between 34 and 66. That much I can say with a probability of 75%. Okay, now at least 75%. Now as said, there is nothing to prove about that, because you can even say that the Chebyshev's theorem says that 2 standard deviations. So I have here only written that 2 standard deviation means how many data points will fall within that. So at least 75% data points. So if I consider 100 new download, upcoming new download, next downloads, then among them 75% will fall in this this much to this much range. Okay, there will be few days. If I consider downloads for next 100 days rather than saying 100 downloads, then among 100 days, on 75% of the day, at least 75 days or maybe more than that, I will have download from 34 to 66. Okay, that is what Chebyshev's theorem says. But let us just calculate it. So we want to find the probability that the number of downloads will be within k standard deviation of the mean, where k is determined by the range that we are given. So here I am given the range that find the probability so that the range is more than 36 but less than 66, 34 but less than 66 means the range is 34 to 66, right? So indirectly I am given the range that 50 minus k, because this is the lower range, so it will be mu minus k into standard deviation. Mu is 50, so 50 minus k into standard deviation is 8, so 8 should be equal to 34. And similarly, this is mu plus k times standard deviation, so that is 50, mu is 50, standard deviation is 8 plus k times standard deviation, that should be equal to 66 because that is my higher range. Okay, and if I solve both these equations, that here 50 minus k into 8 should be 34, or that means 8k, that should be equal to 50 minus 34, that is 16, so k is equal to 2. So I am getting that is 2. And similarly here also, for upper bound also, 50 plus k into 8, that is equal to 66, or that means k8 equals to 66 minus 50, or k into 8, that is equal to 16, or k equals 2 again. So that means what this range is given to me, 34 to 66 download. Now I have found how many standard deviation less than or greater than that is from my mean, that is 50. So it is 50 minus 8 multiplied by 2, right? So that is 34, and it is 50 plus 8 multiplied by 2, that is 66, right? So I have found that is 2 standard deviation region, but the Chebyshev's theorem says that if it is 2 standard deviation region, then the probability that a data point will fall within that, or a new download, the number of downloads for a new 100 days will fall within that region is 1 minus 1 upon k square. K equals 2. So 1 minus 1 by 4. 1 minus 1 by 4 is 3 by 4.75. So we can assert that there is at least 75% probability that there will be more than 34 but less than 66 daily downloads. So you should provide a server which can support, say, more than 34, maybe around 40 for safety, and less than 66. So there also you keep it slightly higher, at 70, so that it can support the required number of downloads. Now you can understand that how important this can be for certain apps, for say Google, who is running entire Play Store on which there are millions of apps, and total number of downloads per day goes into billions. So they have this kind of algorithm which predicts that this app will require this much server space, this app will require this much server space and bandwidth, and accordingly they charge the maker of that app. Okay, so and therefore the person who is downloading, you have seen that whether you are trying a completely new app which is just being downloaded maybe 20 times per day, or whether you are trying some very popular app like WhatsApp or something which is being downloaded millions of times a day, your time for installation on your Android phone remains more or less equal. So it is not that a more popular app takes many hours for downloading because you have to wait in a queue. So obviously more server resources have been allocated to that, right? So this is very important concept about Chebyshev's theorem. One other is coefficient of standard deviation. Okay, now that is nothing to do with that theorem, so we can do that separately, and then we will do this code. Okay, so in next lecture we will take care of this topic. Thank you.